Stanford. Algebra, lesson 6. So I think the last thing we did in lecture 5 was the binomial theorem. We proved that if you take x and y can be variables, numbers, any quantities at all, where in a ring where you can multiply them and add them and so forth, x plus y to the n is always, you can expand it as a sum of powers of x and powers of y with some coefficients. And at each step, the power of x goes down by 1. Power of y goes up by 1. And then finally, you get to x, y to the n minus 1 plus y to the n. But there's some coefficients in here, and we usually write them in this way. I'll write this as n1, n over 2, n over 3, n over n minus 1, and so forth, so we have the binomial coefficient n choose k, that's the way it's read, which is n factorial over k factorial times n minus k factorial. As k goes from 0 up to n. And I remind you, k factorial, for every positive integer k, is the product of the first k positive integers, and 0 factorial is defined to be 1. So the binomial theorem says that x plus y to the n is a sum, x to the I, y to the n minus I goes from 0 up to n, and let me write this as k, x to the k, y to the n minus k, and the coefficient is this binomial coefficient n choose k. And the proof, which is a little bit hard, is by mathematical induction. I'm not going to prove it again. It's in the notes from Monday, but it uses the identity that n plus 1 choose k is n choose k plus n choose k minus 1 for all k between 1 and n. So this is an identity about binomial coefficients that we used when we proved the binomial theorem. Okay, any questions about this? And mathematical induction is a consequence of, and in fact equivalent to, what's sometimes called the minimum principle, which says that every non-empty set of positive integers contains a smallest element. So an empty set has nothing in it, but if you have a set of positive integers, whether it's finite or infinite, no matter how large or how small, it always contains a minimum element, a smallest element. And we use that to prove a lot of results in algebra, and in particular in what's called number theory, properties of the integers. And I'm going to prove some of them for you right now. So the goal today is to prove what's called the fundamental theorem of arithmetic. And we will start. So first, there is what you learned in elementary school, long division. So the first theorem, the division theorem, says you can always divide and get a unique quotient and remainder. So for all numbers a and b in n, remember n stands for the natural numbers, which means the positive integers. There exist unique non-negative integers. Q and R, such that if you divide A by B, you get a quotient B and a remainder R, and the remainder is an integer between 0 and B minus 1. Any questions about this? This is really just formalizing what you learn in school. And the proof is consider, so first I'm going to prove that there always exists some Q and R that satisfy these two conditions. So consider the set S, which is all integers x, non-negative integers, such that x is equal to a minus k times b, where k runs through the set of non-negative integers. So maybe I'll write n naught to be n union 0. This means the set of non-negative integers. N is the set of positive integers. So this also throws in 0, 1, 2, 3, and so forth. So S is the set of all x, which is a non-negative integer. That's what this says, such that x can be written in the form a minus kb for some integer, some non-negative integer k. So S is not empty, because if I choose k equal to 0, x equals a minus 0 times b, that's just a, that is a positive integer. So a is in this set. This set is not empty. And let R be the smallest integer in S. Let me just repeat that. So we have A and B, positive integers, and S is the set of all negative integers, such that X is an integer of the form a minus kb for some non-negative integer. And so S is not empty, because if I take k equals 0, A is in S, so S is not empty. And this means by the minimum principle, S contains a smallest element, R. So R is A minus KB for some non-negative integer. And I want to show that R is less than B. If not, if R is greater or equal to B, then R minus B is greater than or equal to 0. And R minus B is minus KB minus B, which is A minus K plus 1 times B. Right? This is A minus KB minus B. Factor out the B, you get A minus K plus 1B. But this is a number of the form A minus an integer times B. K is non-negative, so K plus 1 is non-negative. So this is in S. Therefore, R minus B is in S, but R minus B is less than R, because I'm subtracting something positive. And this is a contradiction. This contradicts the minimality of R. Chose R to be the minimal element, the smallest element in the set S. So therefore, can't be greater than or equal to B. R is less than or equal to B minus 1. So what I just proved is that there exists integers, let's say Q and R, with A equal to QB plus R, and R is between 0 and B minus 1. Suppose we have other integers, Q prime and R prime, let's say, which also satisfy this relation. Suppose that A is Q prime B plus R prime, where R prime is between 0 and B minus 1. So now we do some elementary arithmetic. If A can be QB plus R and also is Q prime B plus R prime, this equals this. QB plus R equals Q prime plus R prime. But if I rearrange that, that says R minus R prime is Q prime B minus QB, which is Q prime minus Q times B. And here we contradiction and left equals R prime, because R and R prime, these are numbers between 0 and B minus 1. So this number in absolute value is at most B minus 1. But this number in absolute value, if it's not 0, it's bigger than B. It can't be bigger than B if it's equal to something smaller than B. So this has to be 0. So Q prime has to equal Q, and R equals R prime. So Q prime, so Q and R are unique. So again, this is just proving rigorously what you assumed all through school, which is you can divide one number into another, get a quotient and a remainder, and the quotient and the remainder are unique. Okay. Any questions of this? This is 21. Like the division theorem on page 12 of our book. And one consequence of this is a fact which is very important. For example, in computer science, you have the binary representation of integers. Every positive integer is uniquely the sum of distinct of 2. So you take a number, I don't know, 398, and I want to write this as the sum of the distinct powers of 2. Let's see, what are the powers of 2? 1, 2, 4, 8, 6, 16, 32, 64, 128, 250, 56, 5. Well, 512 is too big. The largest power of 2 I can choose is 256. This is 256, and what's left, if I can do this correctly, I think is 142. Now, the largest power of 2, no bigger than 142, is 128. So this is 256 plus 128 plus 14. The largest power of 2, not bigger than 14, is 8. So this is 256 plus 128. See, 14 is 8 plus 6, which is 256 plus 128 plus 8, and 6 is 4, 2. So 398 is 2 to the first power plus 2 squared plus 2 cubed plus 2 to the 7th plus 2 to the 8th. That's writing this number as a sum of distinct powers of 2. And every time you try to use this algorithm, it works. And why does it work? Because the statement is true. But how do we know it's true? Well, it's true if we can prove it. So this is a theorem. And the theorem needs a proof. So how can we prove it? Anyone have any suggestions? How can we try to prove this? Well, sometimes if you can't prove it, then you prove it indirectly. That is, let's try and prove it by contradiction. So suppose if we let S be the set of positive integers where n is not a sum of distinct powers of 2, suppose this set is not the empty set. Right? That means there is some integer which is not a sum of distinct powers of 2. And by the minimum principle, there is a smallest n in the set S. Let me write Let me write as capital N. So there's some number capital N, which is the smallest number that's not a sum of powers of 2. And we know that N is not 1 because 1 is a power of 2 to the power 0 or 0. So N is bigger than 1. Now, the powers of 2, they go to infinity, right? As you take bigger and bigger powers of 2. So let K, all right, say capital K, make some more space over here. So we're assuming we have a number N,
Professor,
which has to be bigger than 1.
Professor, could you put down the previous paper just for 1 second?
Yeah, sure.
Thank you. That's good. I got it now.
All right, so we're assuming there's a number N, which is not a sum of distinct powers of 2. So you have the sequence of powers of 2 going to infinity. And so you can choose the largest power of 2, which is less than N. So N, it's not a power of 2, so it can't be equal to 2 to the K, but it's between 2 to the K and 2 to the K plus 1. Okay? So if any integer N is not a power of 2, it's in between 2 powers of 2.
Can you put the paper down now, Professor?
And N is the smallest integer that's not a sum of distinct powers of 2. Smallest positive integer. So consider the number N minus 2 to the K. If I subtract 2 to the K from this inequality, this is greater than 2 to the K minus 2 to the K, and less than 2K plus 1 minus 2 to the K. Right? 2 to the K minus 2 to the K is 0. And 2 to the K plus 1 minus 2 to the K is 2 to the K, right? 2 to the K plus 1 is 2 times 2 to the K minus 2 to the K equals to K. So I have this number, which is a positive integer. N minus 2 to the K, which is less than N, but N's the smallest number that's not a sum of powers of 2. So N minus 2 to the K is a sum of powers of 2. 2 to the K1 plus 2 to the K2 plus 2 to the, let's say, K sub R. We have exponents such that this number is a sum of distinct powers of 2. And these exponents, right, like the largest one, 2 to the KR, is less than or equal to N minus 2K, which is less than 2 to the K. K sub R is in K. Right? This power of 2, right? So again, N is supposed to be the smallest positive integer, not a sum of powers of 2. And I choose K, so N is between these consecutive powers of 2. It's between 2 to the K and 2 to the K plus 1. If I subtract 2 to the K, I get N minus 2 to the K. It's bigger than 0 and less than 2 to the K plus 1 minus 2 to the K, which is 2 to the K. So this N minus 2 to the K is a positive integer less than N. N is the smallest number, not a sum of powers of 2. So N minus 2 to the K is a sum of powers of 2. And I can write them, they're distinct powers of 2. I can write the exponents in increasing order. The largest 2 to the K sub R, that's in most this number, which is less than 2 to the K. So K sub R is less than K. So that says n is, just bring this to the other side, 2 to the k1, 2 to the k to k2, plus 2 to the k sub r, plus 2 to the k. And here n is a sum of distinct powers of 2. That's it. And it's a nice exercise. So in fact, it's unique. And not only is it unique, but you can extend this to any base. So for every integer b greater than or equal to 2, and every integer n, every positive integer n, you can write n as a sum of powers of b with coefficients between 0 and b minus 1. So to use the citation as the book, you can write n as sum sub k b to the r sub k minus 1 b to k minus 1 down to r sub 1b plus r0. So this is a sum of powers of b where the coefficients, all these coefficients r sub I, are between 0 and b minus 1. So if you take b equal 2, b minus 1 is 1, so the coefficients are just 0 and 1. But let's just do the same example we did a moment ago. But suppose we take b equal 3 and n equal to 398. So I want to write 398 as a sum of powers of 3. So what are the powers of 3? 1, 3, 9, 27, 81, 243, 729. Well, up to 398, the largest power is 243. So let's take that. That's 243, and the remainder is 155. Up to 155, the largest power is 81. So this is 243 plus 81, 74. Up to 74, the largest power is 27. And 74 is 27 plus 47. Up to 47, the largest power is 27, so I can use 27 again. 243 plus 81 plus 27 plus 27 plus 20. 20, the largest power is 9. I can actually take 2 times 9. So I can write 20 is 18 plus 2. That's 2 times 9 plus 2 times 1. So I have 240 plus 81 plus 2 times 27 plus 2 times 3 plus 2 times 1. So this is 1 times 3 to the 5th plus 1 times 3 to the 4th plus 2 times 3 squared plus 2 times 3 to the first power plus 2 times 3 times 3 to the fourth power. This is 398 written to base 3, and the coefficients of the powers of 3, they can only be 0, 1, or 2, and we have 1s and 2s. Okay. Any questions about this? So this is a nice kind of very concrete problem. Maybe right now for a minute or two, an exercise is take a random number, I don't know, 635. Write 635, let's say, to base 2 and to base 3. This means as a sum of powers of 2 with coefficient 0 or 1, as a sum of powers of 3 with coefficients 0, 1, or 2, and maybe also to base 5. This is a sum of powers of 5. So spend a minute or two working this out. It's a good exercise. And I will. Success? Let's see. How do we write 635 as a sum of powers of 2? Can someone tell me?
I got 2 to the 9th plus 2 to the 6th plus 2 to the 5th plus 2 to the 4th plus 2 to the 3rd plus 2 to the 1st plus 2 to the 0.
All right, so let me just check. So 2 to the
Yeah.
9th, I think, is 512. And 2 to the 6th is 64. So it's 586 plus 32. 586 plus 32 is 618, I think. Plus 8 is 26. Is that right? My arithmetic must be off. Let me just double check. Plus 2 plus 1. So this is 40, 104, 500. This seems to be not quite right, right? So let's see. 635 minus 512 is 123. I can subtract 64, and that's 59. I can subtract 32, and that's 27. I can subtract 16, and that's 11. I can subtract 8, and that's 3, and I can subtract 2, and that's 1. So I think 635 is 512 plus 64 plus 32.
Professor.
Plus 16. No, that's exactly what you said. Maybe my arithmetic here.
Okay, you figure it out.
So 123. $59, $27, $16.
I have a 16 in there. So I have 512, add 64, add 32, add 16.
Oh, that's my
And
mistake. I
8
forgot the
and 2.
16.
Yeah.
Thank you. Yep. No. What you said was exactly right. I just forgot that guy. Plus 16 plus 8. So that's correct. What about if we try to write 635 to base 3? So we have the powers of 3, 1, 3, 9, 27, 81, 243, 729. So you can actually use 243 twice, I think. But anyway, can someone tell me how you expand 635 to base 3? I mean, I could certainly subtract 243. That gives me 9, 3, I think. Is that right? 1392. I can subtract 243 again. That's 914, perhaps. I can subtract from that 81, which is 68. '68 is 54 plus 14. 54 is 2 times 27, and 14 is 9 plus 3 plus 2. If I put that all together, 635 is 2 times 243 plus 80, 2 times 27 plus 9 plus 3 plus 2. So this is as a sum of powers of 2. 2 times 3 to the 5th plus 1 times 3 to the 4th plus 2 times 3 cubed plus 1 times 3 squared plus 1 times 3 to the 1st power plus 2 times 3 to the 0th power. So if I was lucky enough to do the arithmetic correctly, this is the ternary expansion of 635 to base 3. Right? It's a sum of powers of 3 with coefficients 0, 1, or 2. And if I was 635 to base 5, the power is 5. 5 to the 0 is 1. 5 to the first power is 5. 5 squared is 25. 5 cubed is 125. 5 to the 4th is 625. So this becomes actually very easy. 635 is 625 plus 10. So 625 is 5 to the 4th, and 10 is 2 times 5 to the 1st power.
2 times 5 to the 1st.
Okay. Does that look all right? Anyway, this is
Yes.
kind of fun. So this is a consequence of the division algorithm. And again, for people who study computer science, in computer science, you often write integers to base 2, or sometimes to bases with powers of 2, like 16 or 32, depending on the sophistication of the program. Okay. Now, in arithmetic, we talked about the division algorithm. And in general, we say the positive integer b divides a if a is equal to q times b for some integer q. That is, if when you divide b by a, the remainder is 0. So if you say b divides a, it's just what you always mean, like 3 divides 12, because 12 is 3 times 4. And the notation is b, a vertical line a. That's the standard notation for saying this means b divides a. So for example, 3 divides 12. And we b is vertical line with a slash means b does not divide a. So 3 does not divide 14. So and for every integer, positive integer n, 1 always divides n, and always divides n, right? Like 1 divides 6, and 6 divides 6. And we say a positive integer n is prime if its only positive divisors are itself and 1 and n. So for example, 6 is not prime because in addition to 1 and 6, 3 divides 6. 7 is prime because the only divisors of 7, the only positive interdivisors of 7 are 1 and 7. And so in fact, we divide the positive integers into 3. So for n is the set of positive integers, we have the number 1, which is in a class by itself, the prime numbers, and the numbers bigger than 1 that are not prime, which are called composite numbers. So if you look, let's say, at the first 10 integers, 1 is special, 2 is prime, 3 is prime, 4 is divisible by 2, so it's composite. 5 is prime, 6 is divisible by 2 and 3, so it's composite. 7 is prime, 8 is divisible by 2 and 4, it's composite. 9 is divisible by 3, it's composite. 10 is divisible by 2 and 5, so it's composite. And in general, it's an interesting question, given a number, to decide if it's prime or if it's composite. And people have been studying prime numbers for thousands of years. So let me make a few statements about them. First, every integer n bigger than 1 is either prime or it is divisible by some prime. So this is a statement that needs a proof. And you can prove this in many ways. Here's a proof which is based on the following property, which I can write as saying divisibility is transitive. And what I mean by that is if C divides B and B divides A, then C divides A. So this is a kind of a lemma, subsidiary fact. How can we prove this? C divides B and B divides A. If B divides A, that means A is QB for some integer Q. C divides B, B is Q prime C for some integer q. If I take this and plug it into the first equation, a, which is qb, is q times q prime c, which is q prime times c. A is a multiple of c. So that's the proof of this statement. If c divides b and b divides a, then c divides a. And how can I prove that? To show divisibility, to show that every number is divisible by a prime. So suppose not. So every number bigger than one. So suppose we let S be the set of all integers bigger than 1 and not divisible by a prime. Right, so let S be the set of all integers bigger than 1 that are not divisible by a prime. I'm going to show that's empty. So I can prove this again by contradiction. And if S is not empty, then there's a smallest integer, capital N, in S. And prime. So let me do this. Start so I have more space. So I'm letting S be the set of all integers bigger than 1 and not divisible by any prime. So if S is not the empty set, then S contains a smallest element called capital N. So N is a number not divisible by a prime, which means N itself is not a prime, because every number divides. So, but if N is not prime, that means N has a divisor little n different from 1 in capital. That is, N is equal to Q times little n.
Can you repeat that sentence again, Professor?
Sorry?
Can you repeat that sentence?
Yes. So let S be the set of all numbers bigger than 1 that are not divisible by a prime. I want to show this is the empty set. There's nothing in there. That every number bigger than 1 is divisible by a prime. But if S is not the empty set, then by the minimum principle, it contains the smallest element, capital N. So I have this number capital N, which is not divisible by any prime. But every number divides itself, so capital N is not a prime, right? Because if N were a prime, it would divide itself, it wouldn't be in that S. So it's not a prime. And what is the definition of a number that's not a prime? It's a number that has a divisor different from itself in 1. That is, there's a divisor little n, which is strictly between 1 capital N. And N is Q times little n. But N is less than capital N. And capital N was the smallest number not in S. So N is not in S, which means there is a prime P that divides N. N is divisible by a prime. So N is R times P for some R. And if I put these two statements together, I get N is Qn, which is QRP, and P, a prime, divides N. And that's a contradiction. Because n is not divisible by a prime. So this set S has to be empty. Every number in 1 is divisible by a prime. Any questions about that? Okay, now so we can start to list the primes. It's a lot of fun to try and find primes. And it's a natural question to ask whether this list stops after some finite number of steps or whether it goes on forever. And this is a question that actually Euclid proved. He might not have, but he certainly included it in his book 2,500 years ago. There are infinitely many different primes. So Euclid's theorem says this list infinitely many prime numbers. In the proof, I can divide it up into 2 steps. So let P1, P2, P3, up to, let's say, P sub k be prime numbers. Multiply them together. P1 times P2 times P3 up to P sub k. So multiply them all together and add 1. And call that number n. Right? So what can I say about n? First of all, 1 plus something positive, so n is bigger than 1. And if you divide n by one of these primes, n is something times prime, because it's one of these, you get a remainder of 1. So if you divide this number by any one of its primes, the remainder is 1. So n is not divisible by any of these k primes. But n is divisible by some prime, because we just proved that every number bigger than n is divisible by a prime. So there exists a prime, I'll call it P sub k plus 1, that divides n. And this new prime is different from all the old primes. Right? I started with k primes, multiply them together and add 1. I get some positive integer n big 1. It's not divisible by any of these primes, because divided by any of these k primes, you get a root of 1. But this is divisible by some prime, because every integer is divisible by a prime. Every integer bigger than 1. So I have a prime pk plus 1 that's different from all these. And if you think about it, this proves there have to be infinitely many primes. Right? So what we just proved is,
Wait, can you go back to the last sentence of that paper?
sure. This number n isn't divisible by any of these k primes. It always leaves a remainder of 1 if you divide by any of these k primes, but it's divisible by some prime. I'll call it p sub k plus 1. So this is a prime from all of these. So given any finite of primes, there is another prime not in the set. Means the number of primes has to be infinite. Because if you only had if there are only finitely many primes, multiply them together, add 1, and you get a new prime, which would be a contradiction. So this is the very elegant proof of Euclid's theorem. Okay, any questions about that? This is really one of the most fundamental results of mathematics. Okay. So let's recall that the notation, if I write D vertical bar A, this means D divides A, or another way of saying this is D is a divisor of A. And if you have two difference B, if D divides A and D also divides B, then D is called a common divisor of A and B. So for example, 3 is a common divisor of 42 and 48. Because 42 is 3 times 14 and 48, 3 times 16. So 3 is a common divisor of 42 and 48. 6 is also a common divisor. Of 42 and 48. Because 42 is 6 times 7 and 48 is 6 times 8. And the difference in this example between 3 and 6, they are both common divisors of 42 and 48, but 6 is the greatest common divisor. It's the largest common divisor. So the GCD, which stands for greatest common divisor of positive integers or integers A and B, is simply the greatest or the largest common divisor A and B. And it's denoted by A and B in parentheses. So for example, the greatest common divisor of 42 and 48 is 6. The greatest common divisor of 84 and 63 is what? Huh. Can anyone tell me what's the greatest common divisor of 84 and 63?
21.
21. Because 84 is 21 times 4. 63 is 21 times 3. And there's nothing bigger that divides both of those numbers. The greatest common divisor of 84 and 64, what is that? So the greatest common divisor of 84 and 63 is 21. What's the greatest common divisor of 84 and 4 and 6? Well, let's see, 1 is a common divisor. They're both even, so 2 is a common divisor. You can check that 4 is a common divisor. What about, well, 5 is certainly not, because that's easy to tell. And what's the greatest common divisor?
Would it be 4?
Yeah, it's 4, because let's see, 84 is 4 times 21. 64 is 4 times 16. And yeah, that's the best you can do. What about 84 and 65? What's the greatest common divisor of those two numbers?
Is it going to be 1?
Yeah, because there's nothing divides, no number bigger than 1 divides either of these two. And this is an important example. We say that integers a and b are relatively prime if the greatest common divisor of a and b is 1. So 84 and 65 are relatively prime. Yeah. And it's actually an interesting problem given to users to show if they're relatively prime, or if they're not, to show that to compute their greatest common divisor. If you take a beginning class computer science, one of the earliest problems you learn to solve on the computer is to compute the greatest common divisor of two positive integers. And computers are relatively modern, but the algorithm, the computer program, actually comes from Euclid. So these are all ancient problems. There is one extremely important and useful theorem about greatest common divisors of two numbers a and b, which is the following. So this is a theorem, section 2023, which is page 13 in the text. For any integers, positive integers a, b, there exist integers u and v, necessarily positive, almost certainly not, such that the greatest common divisor of a and b is a sort of integer linear combination of a and b. So you can always write the common divisor of two numbers as this integral combination of the numbers with integer coefficients. And the proof, like almost everything that we're doing now, uses the minimum principle. Suppose we let A be the set of all positive integers x that you can write in the form ma plus nb, some integers m and n, z. So for example, the integer is 1 times a plus 0 times b, the form, so that's an a. Integer b, which is 0 times a plus 1 times b, also in the set, capital A. So A is not empty. So there are positive integers in this set. Let D be the smallest positive integer in the set A, right? This is a non-empty set of positive integers. So by the minimum principle, it contains a smallest element. So D is equal to UA plus VB, because it's in a set, some integers, there's U and V. Now I claim that this number D divides X for all X in the set A, that every number in this set is divisible by X, A. And why is it true? So by the division algorithm, X is QD plus R, or this remainder R is less than D. It's between 0 and D minus 1.
Can you pull the picture down?
Oh, sorry. So this means that R is X minus QD. X is of the form MA plus NB. D is 2A plus VB. So R is this difference, but I can write this as this is M minus QU times A, and N minus QV times B. So this is a linear combination integer coefficients of A and B. If R is different from 0, then R is some positive number is in A, and R is less than D, which is impossible. It's a contradiction because D was the smallest number in this set. So R can't be 0. R can't be non-zero. So that means R is equal to 0 and X equals Q times D. That is, D divides X. So what we just proved is that this number D divides every element in the set. I claim that this number D is in fact the greatest common divisor of A and B. Why is that? Well, A is in the set, so D divides A. B is in the set, D divides B, so D is certainly a common divisor of A and B. Which means D is less than or equal to the greatest common divisor. This is a common divisor. This is the biggest one, so D is less than or equal to this. On the other hand, D is equal to UA plus VB. And we have, if suppose we let's say D prime be the greatest divisor of A and B. So D prime divides A, and D prime divides B. That means D prime divides U times A and V times B, and their sum. So D prime divides D. Any common divisor of A and B divides D. So D prime, which is AB, is less than or equal to D. So I have D is less than or equal to the greatest common divisor, and the greatest common divisor is less than or equal to D. And the only time you have two numbers and each is less than or equal to the other means they're equal. And that's the proof. So this is a very useful fact that the greatest common divisor, two numbers, is an integral linear combination of the numbers. And we can use that to prove something. Again, a great deal of this is sort of modular, but a lot of this goes back to Euclid. We can prove what is sometimes called Euclid's algorithm, Euclid's lemma. It says, let P be a prime number if P divides the product of two integers, A times B, then either P divides A or P divides B. Right? It's like saying if you have a molecule, it's made up of atoms, and your atom is in the molecule. So if P divides a product, it divides one or the other, or maybe both of the factors, if P is a prime. And the proof goes as so proof. If it divides A, we're done. So we have to show that if P doesn't divide A, then it better divide B. If P does not divide A, then the greatest common divisor of P and A has to be 1. Because what is the greatest common divisor of two numbers? It's the largest integer that divides both of them. Now, P is a prime. To say that P is a prime means that the only divisors are itself and 1. So the only divisors of P are 1 and P. So the greatest common divisor can only be 1 or P. But if P doesn't divide A, the greatest common divisor is not P, so it has to be 1. If P and A have greatest common divisor 1, that means that 1 will be written as this linear combination U times A plus V times P. You can write 1 in this form. Multiply equation by B. Get B is U times AB plus VPB. And what was our hypothesis? What did we start with? P divides AB. So AB is Q times P for some Q. So take this expression and plug it in here. So B is U times AB. That's U times Q times P plus VPB. Factor of P out of the question. This is UQ plus VB times P. B is P times something. It means P divides B. So that is the proof of Euclid's lemma. If a prime divides a product of two numbers, then it divides one of the factors, right? So this is not true for numbers that are not prime. Let me just give an example. So let me just repeat. Euclid's lemma says that if P is prime and P divides A, then P divides A, or P divides B. So suppose we take the number A to be 15 and B to be 14. So A times B is 14, 15. That's 210. 210 is 6 times 35. So we have 6 divides 14 times 15. 6 does not divide 14. 6 does not divide 15. So here we have an example. A number divides the product of two integers, but it doesn't divide either one of them. And the reason why that is because 6 is not a prime. 6 is composite. Composite means prime. So Euclid's lemma is a statement that applies only to prime numbers, not to composite. Okay. Any questions about this? This is all very pretty arithmetic, and it's very important to know. Let me remind you, let's see, I have office hours today and tomorrow at 1:30. Monday is President's Day. CUNY is closed and we don't have a class. So our next class is 1 week from today on Wednesday, the 23rd of February. That's it. Right. Any questions about any of this? Again, I have two office hours come in. As I say, very few people follow up. That I can arrange other time appointment if you can't make one of those regularly scheduled office hours. I should also add this is officially called a hybrid class, and it may be that some of the exams or final exams I'm going to have to give in person on campus. So if that is a severe problem for anyone, let me know. I'm not sure about this yet, but it may be that for a hybrid class, it's optional or it's required. I don't know. But if for some reason it's not possible for you to come to campus to take an exam, let me know by email. Okay. If there's nothing else, then we are done for the day. Stay well, everyone. Next lecture is a week from today. Bye all. Bye all.
Thank you, Professor.
Have a good rest of the week, Professor.
Thank you.
Thank you,
You
Professor.
too.